Chapter 6, Recursive Functions. In this chapter we introduce recursion, the basic mechanism for looping in Haskell. We start with recursion on integers, then extend the idea to recursion on lists. Consider multiple arguments, multiple recursion and mutual recursion, and conclude with some advice on defining recursive functions. Basic concepts. As we have seen in previous chapters, many functions can naturally be defined in terms of other functions. For example, a function that returns the factorial of a non-negative integer can be defined by using library functions to calculate the product of integers between 1 and the given number. Fac is a number from int to int. Fac of n is defined as a product of the list from 1 to n. In Haskell, it is also permissible to define functions in terms of themselves, in which case the functions are called recursive. For example, the factorial function can be defined in this manner as follows. Fac goes from int to int. Fac of 0 is 1. Fac of n is n times fac of n minus 1. The first equation states that the factorial of 0 is 1 and is called a base case. The second equation states that the factorial of any number is given by the product of that number and the factorial of its predecessor, and is called a recursive case. For example, the following calculation shows how the factorial of 3 can be computed. Note that even though the fac function is defined in terms of itself, it does not loop forever. In particular, each application of fac decreases the non-negative integer argument by 1 until it eventually reaches 0, at which point the recursion stops and the multiplications are performed. Returning 1 as the factorial of 0 is inappropriate because 1 is the identity for multiplication. That is, 1 times x is x and x times 1 is x for any integer x. For the case of the factorial function, the original definition using library functions is simpler than the definition using recursion. However, as we shall see in the remainder of this book, many functions have a simple and natural definition using recursion. For example, many of the library functions in Haskell are defined in this way. Moreover, as we shall see in chapter 16, defining functions using recursion also allows properties of those functions to be proved using the simple but powerful technique of induction. Another example of recursion on integers considers the multiplication operator asterisk used above. For efficiency reasons, this operator is provided as a primitive in Haskell. However, for non-negative integers, it can also be defined using recursion on either of its two arguments, such as the second. Multiplication is an operator from int to int to int. N times 0 is 0, n times n is m plus n times n minus 1. For example, 4 times 3, applying times. That is, the recursive definition for the asterisk operator formalizes the idea that multiplication can be reduced to repeated addition. 6.2 Recursion on lists. Recursion is not restricted to functions on integers, but can also be used to define functions on lists. For example, the library function product used in the preceding section can be defined as follows. Product goes from a list of a's to a, where a is a number. Product of the empty list is 1. Product of n n's is n times product of n's. The first equation states that the product of the empty list of numbers is 1, which is appropriate because 1 is the identity for multiplication. The second equation states that the product of any non-empty list is given by multiplying the first number and the product of the remaining list. For example, product of 2, 3, 4 is 2 times the product of 3, 4, and so on. Recall that lists in Haskell are actually constructed one element at a time using the cons operator. Hence 2, 3, 4 is just an abbreviation for 2 cons, 3 cons, 4 on the empty list. Another simple example of recursion on lists. The library function length can be defined using the same pattern of recursion as product. Length is a function from a list of a's to int. Length of the empty list is 0. Length of something const to x's is 1 plus the length of x's. That is, the length of the empty list is 0, and the length of any non-empty list is the successor of the length of its tail. Note the use of the wildcard pattern underscore in the recursive case, which reflects the fact that calculating the length of a list does not depend upon the values of its elements. Now, let us consider the library function that reverses a list. This function can be defined using recursion as follows. Reverse of a list of a's goes to a list of a's. Reverse of the empty list is the empty list. Reverse of x on x's is reverse x's plus the list x. That is, the reverse of the empty list is simply the empty list, and the reverse of any non-empty list is given by applying the reverse of its tail in a singleton list. And a singleton list comprising the head of the list. For example, reverse of 1, 2, 3, applying reverse. Yeah, we get the point. In turn, the append operator plus used in the above definition of reverse can itself be defined using recursion on its first argument. Plus is from a's to a's to a's. The empty list plus y's is y's. Okay, for example, that is, the recursive definition for formalizes the idea that two lists can be appended by copying elements from the first list until it is exhausted, at which point the second list is joined on at the end. We conclude this section with two examples of recursion on sorted lists. First of all, a function that inserts a new element of any ordered type into a sorted list to give another sorted list can be defined as follows. First of all, a function that inserts a new element of any ordered type into a sorted list. Insert from insertion sort. You can write cons without parentheses. I don't think he's shown that before. That is, inserting a new element into an empty list gives a singleton list, while for a non-empty list, the result depends upon the ordering of the new element x and the head of the list y. In particular, if x is smaller than or equal to y, then the new element x is simply prepended to the start of the list. Otherwise, the head y becomes the first element of the returning list, and we then proceed to insert the new element into the tail of the given list. For example, we have insert 3 into 1, 2, 4, 5. 1 cons insert, applying insert 1, 2, insert 3. Using insert, we can now define a function that implements insertion sort, in which the empty list is already sorted, and any non-empty list is sorted by inserting its head into the list that results from sorting its tail. In which the empty list is already not sorted, any non-empty list is sorted by inserting its head into the list that results from sorting its tail. Wow. For example, I sort 3, 2, 1, 4, applying I sort. Multiple arguments. Functions with multiple arguments can also be defined using recursion on more than one argument at the same time. For example, the library function zip takes two lists and produces a list of pairs is defined as follows. For example, zip of ABC and 1, 2, 3, 4, applying zip. Note that the two base cases are required in the definition of zip because either of the two argument lists can be empty. As another example of recursion on multiple arguments, the library function drop that removes a given number of elements from the start of the list is defined as follows. Again, the two base cases are required for one for removing 0 elements and one for attempting to remove elements from the empty list. Multiple recursion. If functions can also be defined using multiple recursion, in which a function is applied more than once in its own definition. For example, recall the Fibonacci sequence 0, 1, 1, 2, 3, 5, 8, 13, in which the first two numbers are 0 and 1, and each subsequent number is given by adding the preceding two numbers in the sequence. A function that calculates the nth Fibonacci number for any integer n greater than or equal to 0 can be defined using double recursion as follows. As another example, in chapter 1 we showed how to implement another well-known method for sorting a list known as quicksort. That is, the empty list is already sorted, and any non-empty list can be sorted by placing its head between the two lists that result from sorting those elements of its tail that are smaller and larger than the head. This is multiple recursion because we use qsort twice in the definition of the recursive case, I think. That is, the empty list is already sorted, and any non-empty list can be sorted by placing its head between the two lists that result from sorting those elements of its tail that are smaller and larger than the head. Mutual recursion. Functions can also be defined using mutual recursion, in which two or more functions are defined recursively in terms of each other. For example, consider the library functions even and odd. For efficiency, these functions are normally defined using the remainder after dividing by 2. However, for non-negative integers, they can also be defined using mutual recursion. That is, 0 is even but not odd, and any other number is even if its predecessor is odd, and odd if its predecessor is even. Similarly, functions that select the elements from a list at all even and odd positions counting from 0 can be defined as follows. Similarly, functions that select the elements from a list at all even and odd positions counting from 0 can be defined as follows. What? I don't get that. For example, evens of A, B, C, D, E, applying evens, A of odds. Yeah, okay. I think I get it. So with evens, you just take the first one and then the odds from x's. Okay. I find this one hard to wrap my head around. Recall that strings in Haskell are actually constructed as lists of characters. Hence, ABCDE is just an abbreviation for ABCDE. Advice on recursion. Defining recursive functions is like riding a bicycle. It looks easy when someone else is doing it. It looks easy when someone else is doing it. May seem impossible when you first try to do it yourself, but becomes simple and natural with practice. In this section, we offer some advice for defining functions in general and recursive functions in particular, using a 5-step process that we introduce by means of 3 examples. Example: product. As a simple first example, we show how the definition given earlier in this chapter for the library function that calculates the product of a list of numbers can be systematically constructed in a stepwise manner. Step 1, define the type. Thinking about types is very helpful when defining functions, so it is good practice to define the type of a function prior to starting to define the function itself. In this case, we begin with the type. Product goes from a list of ints to int. That states that product takes a list of integers and produces a single integer. As in this example, it is often useful to begin with a simple type, which can be refined or generalized later on in the process. Step 2, enumerate the cases. For most types of argument, there are a number of standard cases to consider. For lists, the standard cases are the empty list and non-empty lists, so we can write down the following skeleton definition using pattern matching. Product of the empty list is product of n ends. For lists, enumerate the cases following skeleton. Okay, for non-negative integers, the standard cases are 0 and n. For logical values, they are false and true, and so on. As with the type, we may need to define the cases later on, but it is useful to begin with the standard cases. Define the simple cases. By definition, the product of 0 integers is 1, because 1 is the identity for multiplication. Hence, it is straightforward to define the empty list case. As in this example, the simple cases often become base cases. Step 4, define the other cases. How we calculate the product of a non-empty list of integers. For this step, it is useful to first consider the ingredients that can be used, such as the function itself, product, the arguments, and ends, and library functions of relevant types, plus, negative, times, and so on. In this case, we simply multiply the first integer and the product of the remaining list of integers. As in this example, the other cases often become recursive cases. Step 5, generalize and simplify. Once a function has been defined using the above process, it often becomes clear that it can be generalized and simplified. For example, the function product does not depend on the precise kind of numbers to which it is applied, so its type can be generalized from integers to any numeric type. Product goes from a list of numbers to a. In terms of simplification, we will see in chapter 7 that the pattern of recursion used in product is encapsulated by a library function called fold_r, using which product can be redefined by a single equation. Product is fold_r times 1. Why does he keep giving examples using fold when we haven't learned that yet? In conclusion, our final definition for product is as follows. Product goes from num a to a list of a's to a's. Product fold_r times 1. This is precisely the definition for lists from the standard prelude, except that for efficiency reasons, the use of fold_r is replaced by the related function fold_l, which is also discussed in chapter 7. Example, drop. As a more substantial example, we now show how the definition given earlier for the library function drop that removes a given number of elements from the start of a list can be constructed using the 5-step process. Step 1, define the type. Let us begin with a type that states that drop takes an integer and a list of values of some type A and produces another list of such values. Drop goes from int to a to a list of a's to a list of a's. Note that we have already made 4 design decisions in defining this type, using integers rather than a more general numeric type. For simplicity, using currying rather than taking the arguments as a pair. For flexibility, supplying the integer argument before the list argument. For readability, an expression of the form drop n x's can be read as drop n elements from x's. And finally, making the function polymorphic in the type of the list elements for generality. Step 2. Enumerate the cases. As there are two standard cases for the integer argument 0 and n, and two for the list arguments, the empty list and x cons x's, writing down a skeleton definition for the function using pattern matching requires 4 cases in total. Define the simple cases. By definition, removing 0 elements from the start of any list gives the same list, so it is straightforward to define the first 2 cases. Drop 0 of the empty list is the empty list. Drop 0 x cons x's is x cons x's. Drop n of the empty list. He's going to define that later. Attempting to remove one or more elements from the empty list is invalid, so the third case could be omitted, which would result in an error being produced if this situation arises. In practice, however, we choose to avoid the production of an error by returning the empty list in this case. Is that true for the... Oh, okay. Step 4, define the other cases. How we remove one or more elements from a non-empty list? By simply removing one fewer elements from the tail of the list. Step 5, generalize and simplify. Because the function drop does not depend on the precise kind of integers to which it is applied, its type could be generalized into any integral type, of which int and integer are the standard instances. Integral b. For efficiency reasons. However, this generalization is not in fact made in the standard prelude, as noted in section 3.9. In terms of simplification, the first 2 equations for drop can be combined into a single equation that states that removing 0 elements from any list gives the same list. In terms of simplification, the first 2 equations for drop can be combined into a single equation that states that removing 0 elements from any list gives the same list. Moreover, the variable n in the second equation and x in the third can be replaced by the wildcard pattern underscore, because these variables are not used in the bodies of their equations. In conclusion, our final definition for drop is as follows, which is precisely the definition from the standard prelude. Example, init. As a final example, let us consider how the definition for library function init that removes the last element from a non-empty list can be constructed. Let us consider how the definition for the library function init that removes the last element from a non-empty list can be constructed. Okay, define the type. We begin with a type that states that init takes a list of values of some type A and produces another list of such values. Init goes from A's to A's. Enumerate the case. As the empty list is not a valid argument for init, writing down a skeleton definition using pattern matching requires just one case. Step 3. Define the simple cases. Whereas in the previous 2 examples, defining the simple cases was straightforward, a little more thought is required for the function init. By definition, however, removing the last element from a list with one element gives the empty list, so we can introduce a guard to handle this simple case. Whereas in the previous 2 examples, defining the simple cases was straightforward, a little more thought is required for the function init. By definition, however, removing the last element from a list with just one element gives the empty list. So we can introduce the guard to handle this simple case. Okay. The library function null a bool decides if a list is empty. Step 4. Define the other cases. How can we remove the last element from a list with at least 2 elements? By simply retaining the head and removing the last element from the tail. Generalize and simplify. The type for init is already as general as possible, but the definition itself can now be simplified using pattern matching rather than guards, and by using a wildcard pattern in the first equation rather than a variable. Again, this is precisely the definition from the standard prelude. 6.7 Chapter Remarks. The recursive definitions presented in this chapter emphasize clarity, but many can be improved in terms of efficiency or generality, as we shall see later on in the book. The 5-step process for defining functions is based on 8. Maybe I shouldn't have clicked that. Programming by numbers, a programming method for novices. Wow, that works rather well. 6.8 Exercises. How does the recursive version of the factorial function behave if applied to arguments of negative arguments such as -1? Modify the definition to prohibit negative numbers by adding a guard to the recursive case. Okay, so I'm guessing it's going to go into an infinite loop. Let's take a look how it was defined. Wait, it was the factorial function, yeah? Or, oh no. Factorial function. Maybe we can, as an exercise, just try and rewrite that. Okay. So factorial of 0 is 1. Maybe first we need to do the type. Fac goes from, let's just do the non-general into int. Fac of 0 is 1. Fac of n is n times fac of n minus 1. Wait, oh. 3 times 2 times 1 is 6, yes. Now, if we give a negative number, it's going to loop forever, right? Because it's always subtracting. Wow. Wait, ints are non-negative? Or... Oh no, it's doing that thing again where it's applying. Wow, okay, so... Oh no, I don't know how to stop this, okay. Okay, so I think, oops. N is less than or equal, no, less than 0 is error. We haven't, X is, but this is non-exhaustive, so I don't really know. Exception, non-exhaustive patterns, but does it still work for 3? Yes. So, are guards always preferred to if statements? And if so, why are if statements even in language then? Exercise 2. Define a recursive function sum down from int to int that returns the sum of non-negative integers from a given value down to 0. For example, sum down 3 should return the result 3 plus 2 plus 1 plus 0 is 6. Okay. So sundown, then the base case. Oh, or how does he say? First write the skeleton. So sundown of 0 is 0, and sundown of x is x plus sundown of x minus 1. Oops. Sundown of 3 is 6. And then I think we should add a guard. X is greater than 0. Okay. 3. Define the exponentiation operator caret. We need to define it, so we'll just write it as a function because I can't figure out how to do that. And so x, or maybe we can just call it pow. Pow goes from int to int to int. Base cases, pow of 0, x, 0 to anything is 0. Pow of x to the 0 is 1. Pow of x to the y is x times pow of x to the y minus 1. 2 to the 3rd is 8. Yes, that seems right. Show how the expression 2 to the 3rd is evaluated using curve. How do you write comments again in Haskell? Nope. Okay, pow of 2, 3, 2 times pow of 2 and 2 is 2 times pow of 2 and 1 is 2 times 2 times 2 pow of 2 and 0, 2 times 2 times 2 times 1. Okay. Oh my god. So, and if we do 3 to the 0, it says 1. I think that's good. Maybe we can simplify it. I don't know. Define a recursive function Euclid from int to int to int that implements Euclid's algorithm for calculating the greatest common divisor of two non-negative integers. If two numbers are equal, this number is the result. If two numbers are equal, this number is the result. Otherwise, the smaller number is subtracted from the larger, and the process is then repeated. For example, Euclid 6 and 27 is 3. If the two numbers are equal, this number is the result. Euclid
Otherwise, the smaller number is subtracted from the larger, and the process is then repeated. Okay, wait, so we need to add another guard. Or we can define smaller xy is otherwise is Euclid Euclid of A and B, where A is larger xy, or wait, let's do a larger minus smaller, and smaller, where L is, let's do, yeah, let's rename these into larger and smaller, where L is larger xy. Can you, I think you can do S is smaller xy. Okay, that did not parse. Remove. So I looked up how to do where with multiple arguments, and it says is so Haskell is indentation sensitive, apparently. Euclid of nope, of 6 and 27 is 3. So that works. How many more exercises are there? Okay, let's do one more, and then I'm gonna eat breakfast. Using the recursive definition given in this chapter, show how length, drop, and init are evaluated. Oh, that's boring. Without looking at the definition from the standard prelude, define the following library functions on lists using recursion. Okay, let's do that one. Okay, and goes from a list of bools to bool. So I think we could do this with a fold, but let's not do that because he said we need to use recursion. End of the empty list. Is that decide if all logical values in a list are true? So in the empty list, I think the answer is true because there are none. End of x and x's is x and end of x's. Okay, so that already exists, so let's call it handle. Oh. Oops. Handle. Okay, that works. Let's try and do it with the fold. We should probably call them B's instead of X's, maybe. I don't know. Is fold R of wait. So it takes a, okay, so I think this is going to be and takes a base case and a list. Oops, nope. That works. That's cool. And then I think we could even write it like this, right? Oh my God. That's pretty cool. That's very unreadable though. I don't know why point-free functions exist. Concatenate a list of lists. Concat. From a list of lists of A to A. Concat. And the empty list is the empty list. Concat of x to x's is x. Yeah. Let's do it with the fold again. Fold R is not in scope. Oh, Fodler. Variable not in scope O. Excuse me. Huh? Oh, I accidentally put an O under there. Oh, why do I keep writing can cat instead of con cat? Boom. Okay, produce a list with n identical elements. My replicate goes from into A to a list of A's. My replicate 0 anything. Wait, is the empty list, and my replicate of n and A is A plus plus my replicate minus 1 of A. Boom. Select the nth element of a list. So again, I don't know how to do operators. Nth x is x, no I. Oops. Oh my god. List of A's to int to A. Then oops. Is x and the is nth of x's and I minus 1. Nth of 1, 2, 3, nth of 1, 2, 3, 1. Oops. Okay, that works. Decide if a value is an element of a list. My lm okay, so my lm of anything and any a is false. My lm of x and xx, oh no, I don't think that works. My element of x is a is x is true, otherwise is my lm pattern match is redundant. Huh? What? I don't understand. Oh, that's wrong. Oh yeah, we skip over elements. It should be just this again. Ah, why does it keep doing that? Oh my god. I don't understand. Okay. My LM is chewing 1, 2, 3 is false. What? Oh yeah, what? What have I written here? My LM of A and the empty list is false. But why was it? I don't know. Oh. My LM. Yes, okay. That was a bit embarrassing. Okay, are we gonna do more? I don't think so. It's already been an hour.